matrix. First order of business, we write down the characteristic equation. So the determinant of A minus lambda I is the determinant of minus lambda, 0, minus 4, 2, 4 minus lambda, 2, 2, 0, 6 minus lambda. All right. Now we need to calculate. So that looks like a minus lambda times the determinant of 4 minus lambda to 0, 6 minus lambda. And then minus 4 times the determinant of 2, 4 minus lambda, 2, and 0. All right. Well, that is lambda with a minus times lambda minus 4 times lambda minus 6. Notice I like this trick. Do you guys pick up on what I'm doing? I don't like to write minus lambda if I can help it. I much prefer positive lambdas. So when I multiply these factors out, I just like minus times minus gives me plus, right? That's what I'm doing. So that's that. And then over here, I have minus 4 times, well, let's say minus 2 times 4 minus lambda. All right, so, oh, woo, hey, 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 hey. This is awesome. All right, so, yes. This is minus lambda times lambda minus a 6. Blah, blah, blah. Minus 8, parentheses, times lambda minus 4. I'm going to make a editorial adjustment up here and change that to a plus and a lambda minus 4, so it's easier for you guys to follow. I think that's probably better. So then you see we get 2 times 4 is minus 8. There's a lambda minus 4 both places. I can factor it out. And then what do I got? I've got minus lambda squared plus 6 lambda minus 8 times lambda minus 4. Highly recommend factoring a minus out. So that's lambda minus lambda squared minus 6 lambda plus 8 times lambda minus 4, which is minus, what we got here? That factors, ooh, it factors. That's lambda minus 2 times lambda minus 4 squared. Yay. Because that gives me 2 lambda minus 4s. So this is a 3 by 3 problem. Our eigenvalues are, find lambda 1 equals to 2 and lambda 2 equals to, let me say lambda 1 is 4 and lambda 2 is equal to 2. There, I feel better about that, yeah? This is twice, right? The algebraic multiplicity of 4 here is 2. It's repeated. All right, now let us find the eigenvectors. All right, so we'll do the 2 first. A minus 2i times u1. So that's what? Minus 2, 0, minus 4, 2, 2, 2, 2, 0, 4, U, V, W. Now technically speaking, to be super safe, we should always do row reduction to the reduced row echelon form, and then we can have complete confidence in our solution that we haven't missed anything or misappropriated or misinterpreted the results, right? But we don't really need to go through all that if you just use some common sense. Like common sense here is that the first and the third rows are redundant, right? First and the third rows are redundant. So I can just take my third row and go, all right, so that means that u is equal to minus 2w, right? Because 2u plus 4w equals to 0. So u is equal to minus 2w I get from the third row. And then I will take that and I will put it up into the second row. The second row is that u plus v plus w is equal to 0. Just because there's 2's there doesn't mean you need to keep them. Why make it more complicated? Divide by 2, right? And this tells me that v is minus a w minus a u, which is, by the way, minus w minus parentheses minus 2w, also known as w. So apparently, my u1 vector has the form minus 2w, w, w. Or if you like, w times minus 2, 1, 1. So incidentally, the eigenspace with eigenvalue 2 is the span of minus 2, 1, 1. This is a basis for lambda equals to 2 eigenspace. The eigenspace is the set of all eigenvalues with a particular eigenvectors with a particular eigenvalue, and also one very privileged non-eigenvector the eigenspace has. 0. 0 is in the eigenspace. It's not an eigenvector, right? But that's it. So the eigenspace for eigenvalue 2 here is one-dimensional. It's a one-dimensional eigenspace. How about 4? So if we look at, a minus 4i times u2, let's say, equals to 0, that is minus 4, 0, minus 4, 2, 0, 2. Ooh, look at this. 2, 0, 2 times uvw equals to 0. Now this right here does not require row reduction. It requires common sense. What's the solution? Pick any row you like, right? We've got u plus w is equal to 0. So therefore, w is minus u, let's say. What about v? You guys have a bad habit of getting this part of it wrong. We have to understand our context here is that v is free. So the solution then, u2, has the form u is, v is free, w is minus u. So if I factor u out, I've got u times 1, 0, minus 1, plus v times 0, 1, 0. So then the eigenspace with eigenvalue 4 is the span of those two vectors. You should recognize this calculation. We've done it before. This is the null space basis calculation, right? This is in fact the null space of a minus 4i. That is the eigenspace with eigenvalue 4. It's two-dimensional. In this particular problem, the geometric multiplicity and the algebraic multiplicity of 4, they're matching. They're both 2. All right. So guys, is this matrix diagonalizable? What do you think? So you need some theory that I haven't shared with you guys yet, and next time I'll try to hit the theory more. I'll try to hit the theory harder, but let me just give you a preview. Actually, maybe this is enough. So here's the theory. I forget, I don't have to prove things in here, right? So theory if lambda 1, lambda 2, lambda n are distinct eigenvalues, then corresponding v1, v2, vn eigenvectors are linearly independent. Now that's not quite our situation here, right? That's not quite our situation. But there is another theorem which says that if you have, this is a little bit, it's harder for me to state it. Let me say it this way. If you have v1, vr linearly independent with eigenvalue 1, and if you have w1, ws with lambda eigenvalue 2 not equal to lambda 1, then v1 through vr, w1 through ws is linearly independent. So what I'm trying to say here, guys, is that if we take eigenvectors that have distinct eigenvalues and they're linearly independent with respect to, like, all right, so like this example, I have two eigenvectors for eigenvalue 4, right? Those are clearly linearly independent. They're not multiples of one another, right? I also have an eigenvector with eigenvalue 2, right? And so what I'm telling you is that the theory here tells us that these three vectors that we found are in fact linearly independent, which means that they're actually a eigenbasis, right? So is this matrix that we started with here, A equals to, in example 5, is this a diagonalizable matrix? The answer is yes. Yes, it is, because we have an eigenbasis, and we proved just a minute ago here that if you have an eigenbasis for a matrix, then that matrix is diagonalizable. Okay, fine. I stated it for a linear transformation, but the transformation's diagonalizable if and only if its matrix is diagonalizable. So we can either think about the matrix or the transformation. Truth be told. Questions? All right. So this obviously is the trouble, right? This is the problem. We have to be careful about this. This is where bad things happen. This is where you need to be really careful. If you do this wrong, what happens? You get eigenvalues that are deceiving. They're not really eigenvalues. What happens if I put anything but 4 or 2 here? If I put a 3, what's the answer? A minus 3i times u equal to 0. What's the solution? U equals 0. It is inevitable. Because only for lambda equals to 4 and lambda equals to 2 is the matrix A minus lambda I not invertible. For all other possible lambda, that matrix is invertible, and the only solution to an invertible matrix times vector equal to 0 is the zero solution. So if you think you found an eigenvalue, and then you go look for the eigenvector, and the only solution you're getting there is 0, listen to what the math is telling you. The math is telling you to go back here and fix it. Find out what you multiplied out wrong, because your eigenvalue is not really an eigenvalue. All right? Now, sometimes you guys trick yourself into like this problem. A lot of times I'll see people go, well, there's no v, so v has to be 0. If there's no v in the equations, that doesn't make v 0. That makes v free. The very opposite of being forced to be 0. Right? Very different. Anyway. So, more after break, I suppose. And I'll look at your problems, I suppose. Thanks, guys.